Hi guys, this is Jonathan Lambert of Maths and Stats, and in this video, this is I suppose the first video in this particular series of videos dealing with generating functions. I'm going to try to introduce the concept of generating functions that are associated with sequence through some simple examples. Uh, Really, what I'm actually going to present here is I suppose has been previously encapsulated or captured by Walter Levin in his great book and also on his web page. So albeit I'll do things hopefully a little bit differently. The motivation for what I'm actually going to present from my reading and so on, the Walter Levin page has been a very influential page for me. So what we have so far up to this particular stage is we've considered sequences. We've defined sequences from many particular perspectives. We've defined them and from an arithmetic perspective, whether they're arithmetic sequences or whether they're geometric sequences. And more importantly, we have formula that can calculate the nth term in a particular sequence once we have I suppose once we've figured out whether it's arithmetic or geometric, we can actually calculate the formulas, which give us the nth terms. Uh, but what generating functions allow us to do is allows us to, let's say, is to manipulate these sequences in certain ways, and allows us to add sequences together and to do other types of operations with sequences to give us new sequences, as well as trying to identify the functions that encode the actual sequences themselves. So just to motivate things, let's consider a simple sequence. So this particular sequence that we're going to consider is really the baseline sequence that most other generating functions are going to be developed from. So let's consider the sequence. The sequence is a very simple sequence. It's just a sequence with constant terms. So it's a sequence. The sequence, let's say, 1, 1, 1, 1. So it's all ones. So the sequence is an infinite sequence of ones. Now, what we're going to do first of all is we're going to represent this particular sequence in in a power series with a power series representation, which is simply a polynomial that has a specific structure. So, for example, let me just pull it out of the sky. So, the power series associated with this particular sequence, okay, its power series looks something like this. So all it is it's 1 for the first term. It's really 1 times x to the 0, but x to the 0 is just equal to 1. So 1 times 1 is 1. Plus 1 times x is x. Plus 1 times x squared is x squared. Plus 1 times x cubed is x cubed. Plus and so on forever. Okay. This particular power series, uh, each term, so this particular power series has each term in it, okay, has a specific position, and the position is demarcated or is denoted by the power associated with the indeterminate here. So, for example, this value here is a 1. It's a coefficient of the x0. The coefficient of the x to the power of 1 here is a 1. The coefficient of the x squared is a 1. The coefficient of the x cubed is a 1. So the first term in the series here is a 1. So this represents this one. It's 1 times x to the 0. If I want to find a third term from the power series, if I want to find a third term in the sequence, well, what I do is excuse me, if I don't forget, we start counting from 0. So in this case, this is the 0th term, the first, the second, the third term. So what I do is I go to x to the power of 3 and I look at its coefficient, and that tells me the value or the term in the sequence at position 3 from counting from 0, if that makes sense. So what we have here is, for this simple sequence, its power series looks something like this. Now the question is that this is an infinite power series. Uh, is there any way that we can find a closed form function that basically represents the summation of this particular sequence? And we can actually do that. So let's write down this. So finding, and this closed form function is what's known as the generating function for the power series. So every generating function is associated with a power series, and the coefficients in the power series are, let's say, associated with the terms in the sequence itself. Okay? So finding the generating function, so finding its generating function is quite simple. So what we do is let's give this generating function a name. Okay, let's call it g1. Okay, let's call it g1 of x. Okay, the generating function, the first generating function for my first sequence here. So what we let g1 of x equal is the power series that has encoded the sequence itself. So this is equal to, in this case, 1 plus x squared plus x cubed plus dot dot dot. And what we're going to do here is we'd like to sum up this particular series of power terms. Okay, and there's a little trick that we can use to sum up that particular sequence. Well, what we should notice is this, hopefully, is that if we multiply this power series here by x, let's do that. So let's multiply it by x. So we're going to say x times g1 of x. Now we know what g1 of x is. It's this power series here. So we're going to multiply each term in this series by x. And what happens is x times 1 gives me x, plus x times x gives me x squared, plus x times x squared gives me x cubed, plus, and so on. So the effect is multiplying the original power series by x had the effect of shifting every term in the series, okay, on by one. The one went to an x, the x went to an x squared, the x squared went to an x cubed, the x cubed goes to an x to the 4, and so on. And this is an infinite series. So what we'll do now is that we'll subtract this new series that we've just generated from the first one. So let's do that. So we're going to calculate g1 of x minus x of g1 of x. And let's see what happens. So effectively, we're taking this series away from the first series. And this is the positive version of it. So the negative version will be